Okay, welcome back. We're still in Chapter 2. We're going to go on to Section 2 now. We're going to divide this up into 3 categories, just kind of taking our time working our way through it. That way we don't overload you with all sorts of information and just kind of take it day by day. So again, this section, we're going to divide this into 3 spots. The first part that we're going to use today is we're going to use the density curve to model distributions of quantitative data. We're going to identify the relative locations of the mean and median from a density curve, and then we're going to use the empirical rule, a little typo there, sorry, to estimate the proportion of values in a specified interval, or find the value that corresponds to a given percentile in a normal distribution. That's where we're going to stop. And then part 2, we're going to get into finding the proportion of values in a normal distribution using a table or technology. I'll have those tables for you. And then we're going to find the value that corresponds to a given percentile in order to be using that table. And then we'll wait for the last day. We'll kind of determine whether a distribution of data is approximately normal from graphical and numerical evidence. That's what kind of work on assessing that normality from there. So getting going today. So in Chapter 1, we kind of got, as they call, a kit of different tools for describing distributions, and remember our socks and all that. We're going to add one more step to that. So we already have these types of things. And again, if we're adding the same number to each attribution, we're going to always plot your data, look for the pattern, shape, center, variability, outliers, calculate summaries. We have different things like the standard deviation, the range, the mean, median, all that stuff. And then the next thing is when there's a regular overall pattern, we're going to use a simplified model called a density curve to describe it, is what we're going to do. Now, a density curve, it's always on or above the horizontal axis, always has an area of exactly 1. And the area of the curve and above any interval of values in the axis estimates the proportion of all observations that fall in that interval. Okay, so as we kind of look at a density curve here, converting that data from a dot plot over there, you can see that the overall pattern of this dot plot, the amount of time it takes Selena to get to the bookstore by train each day for the last 1,000 days she worked, can be described, it's kind of by a horizontal line describes that. All right, here, so we're looking at scores, standardized test scores from the Iowa Test of Basic Skills, kind of a smooth curve. You can kind of see that curve kind of going through those. And that's one we're going to really focus on here throughout, okay? Now, the mean of the density curve is the point at which it would balance, okay? And the median, it's kind of equal areas, divides the curve kind of in half is what it does. Now, again, if it's skewed, you'll notice, remember, that the mean gets pulled towards the skewness. So we'll see some graphs looking like that, okay? All right, now a density curve, it's the idealized description of a description of data, okay? So we're going to distinguish between mean and standard deviation of the density curve, and the mean and the standard deviation computed from actual observations is kind of what's there. And the usual notation, now mean, we talked about this before, a lot of times it's x with a bar over it, but what we're going to use here is we're going to use the Greek letter mu. Is what it is, and then the standard deviation is going to be the lowercase sigma, the Greek letter sigma is what we'll use for mean and standard deviation with these curves. All right, so the normal distribution, this is a big one, guys. The normal curve, which comes from normal distributions that we shape this. Now, what we're going to notice is that they're symmetric, single peak. They look like bell-shaped curves that a lot of times referred to. Mu, this mean, and the median are actually going to be the same spot. Okay, and then the standard deviation measures the variability. It's the width of a normal distribution. So we're going to kind of put those in there, and we'll see how those fit in. Now, why normal distributions so important? Here are just a couple of reasons, and previewing a few things, is that a lot of times when you take scores, SAT, ACT, IQ tests, those really come in those shapes, those graphs. If you're doing quality control of measuring like the diameter of a tennis ball, yeah, you're going to see they're not all exactly alike. There's a little variation, but they kind of take that shape. Characteristics in biological populations, such as length of crickets, yields of corn, it's really kind of amazing all the things that this relates to. And again, some other things are good approximations. It's like the proportion of heads when you're tossing a coin. And we're going to use that a lot when we start talking about inference in third quarter when we do chapters 8 through 12. They're really based on that normal distribution. So it's a good thing that we get started on this now. So here's the empirical rule. The empirical rule is basically going to say that, okay, here's your mean. If you go one standard deviation above and below, it's really if it's a normally distributed, about 68% of your values are going to fall within one standard deviation. All right, and then within two standard deviations, 95% of your values should fall within those. And then if you get out to 3 standard deviations away from the mean, that's almost all, 99.7% of your data, almost all. Very rare are you ever outside of 3 standard deviations. And we'll talk about how to use that to determine outliers, those types of things down the road. But just remember that empirical rule. It's the 68, 95, 99.7 rule is what it's referred to. Okay, so remember, the empirical rule, it only applies if it's normal distribution. Okay, well, that's where we're going to stop today. We'll pick up tomorrow with the rest, the second part of section 2. Until then, I'm Mr. Boone.